We are live.
Okay, I'll
A
start.
very good evening to all. So I welcome you today to the iFocus lecture of optics and refraction module. And today we are going to be discussing the identification of unknown lenses, neutralization, Focimeter, and Geneva lens measure. This topic will be covered by Dr. Shreya Tyagi. Today we have our chairman as Dr. Rupal Shah. We welcome you, ma'am. Ma'am
Thank you.
has been a refractive surgeon since 1994. Ma'am, we all know, is fondly described as the mother of smile, and she is the first person in the world to do a one incision smile, and also the first to use the Circle software in a patient for retreatments. Ma'am has trained more than 2,000 ophthalmologists from across the world and has been successfully conducting intensive LASIK training courses, attending by several ophthalmologists every time. Ma'am has many national and international publications and presentations to her credit and is the recipient of numerous awards and gold medals. Once again, we welcome you, ma'am.
Thank you, Dr. Nidhi, for the kind words.
Our speaker for today is Dr. Shreya Tyagi. We have the next slide, please. Dr. Shreya is an undergraduate from the Sikkim Manipal Institute of Medical Sciences and an MS with a gold medal from Gandhi Medical College, Bhopal. She has done her fellowship in cornea and cataract from the Shroff Charity Eye Hospital, Daryaganj. She has trained in refractive surgery under Dr. Rupal Shah, ma'am, and is a survey doctor in the rapid assessment of avoidable blindness. She is currently practicing as a consultant at Center for Sight Eye Hospital, Ghaziabad. Dr. Shreya has performed more than 3,000 cataract surgery procedures, including complicated cataracts, and has trained many fellows in cataract and penetrating keratoplasty surgeries. She has numerous presentations and publications in prestigious national and international conferences and journals.
Thank you so much, ma'am, for such a generous introduction. I'd love to introduce you as well. Please welcome Dr. Kalyanidhi Garda, ma'am, who is the professor and senior advisor currently in ophthalmology of Command Hospital, CHWC. Is my voice echoing?
Yes. It's heard, Shreya.
Okay, ma'am. Ma'am has completed her MBBS in 2002 from AFMC Pune, and then she went on to do her MS in DNB from the same college. Ma'am has done her long-term training in cornea and refractive surgery from RP Center, AIMS. She has had 15 years of experience as ophthalmologist in various service hospitals. Ma'am has multiple achievements to her name. She's published over 35 publications in various national and international journals and has authored 5 book chapters. Ma'am has also presented papers in IST, ISTRS, AIOS, and AIRSI. We welcome you, ma'am.
Thank you, Dr. Shreya. And I think now we hand over you the topic to begin this interesting topic today of neutralization and Geneva lens measure and identification of unknown lenses.
Before you start, Shreya, I think there are two of your
Yes, ma'am.
devices active. So there's
Yes,
a little echo which is coming. So you can maybe switch off one.
I'll just take care of that.
Yeah. It's a pleasure to meet you, Dr. Nidhi.
Thank you so
Thank
much,
you.
ma'am. It's always a pleasure to meet you, ma'am, in conferences and other platforms.
So Shreya, please go ahead.
Yes, ma'am. I'll just take care of the audio for once. I'll take a minute.
Are we ready? Yes.
Yes, ma'am. Am I audible now?
Yes, you're audible.
Okay. Ma'am, am I clearly audible? Can I start?
Yes, you're audible, and the slides are also visible, Dr. Shreya.
Okay.
We can see.
Yes, ma'am. So today's topic is identification of unknown lenses, that is by neutralization, Focimeter, and Geneva lens measure. Coming to hand neutralization, it gives us a rough measure. It is less accurate than lensometers. However, it gives us a good idea in case of small spherical numbers and tells whether a lens is plus, minus, or a toric lens. It basically measures the front vertex power of the lens. By neutralization, what we mean is that two lenses will be said to be neutralizing each other when the combined power of the two equals 0. So the lens that we'll be using for neutralization will be of the same power as the lens that we are trying to know the power of, but the sign will be different. As in the case we can see here that this is a concave lens which is being neutralized by a convex lens, and this is a convex lens which has been neutralized with the help of a concave lens. Now the power of the two would be the same, but the signs will be different. So how do we go about it is that we take the lens and then we see a uniform cross through the lens. The lens has to be held at arm's distance at visual axis, and then it has to be moved vertically, and the horizontal lines are to be observed, and while moving it horizontally, the vertical lines are to be observed. So in this particular diagram, this is what, while we are moving the lens in one direction, the image is moving in the other direction, which tells that this is a convex lens, that it is a plus lens, and vice versa is true in the case of a concave lens. That is, the image is going to move in the similar direction as that of the movement of the lens. When there is no movement, that will depict that neutralization has taken place. So this is a concave lens that the image is moving in the similar direction of the lens movement. Now what happens if in case you're going to rotate the lens and if in case there occurs a scissoring of the image, that means that this is a toric lens. When we rotate it in a clockwise direction and the lines are also rotating in the similar fashion, that means that it's a concave lens. However, if we are rotating it clockwise, but the image is moving anti-clockwise, that means that it is a plus cylindrical axis. The cylindrical lens would be said to be neutralized if in case the two lines are perfectly perpendicular to each other. And in that case, we'll have to mark the cylindrical axis with the help of a ferrite tip. It can also be used to know the ground prism. And in this, it will show that whenever the prism is base up, it will displace the image downwards. And when the base is down, it will displace the image upwards. Base in will be displacing the image outwards, and base out will be displacing the image inwards. So this is how neutralization looks, that we are moving the lenses. However, there is no movement in the image of the cross. So what are the steps of neutralization? The first thing, like we said, that we'll be drawing a cross with its arms perpendicular to each other, and then we are going to determine the principal meridian. So this is especially true when we are neutralizing spherocylindrical lenses. First, we have to firstly eliminate the scissoring movement that is happening, and then we have to mark the cylinder, the particular axis, with the help of a felt tip, and afterwards we start neutralizing the powers. So we neutralize each meridian and we draw a power cross, and then we convert into spherocylindrical power. So this is a video showing how we neutralize the spherical lenses.
Hello friends, today I am going to discuss with you all how can we find out a lens power without using lensometer. And for this we follow a method that is called head neutralization. I am taking this unknown lens power and going to find out its actual power. First of all, we need to determine what type of lens it is. So let's check, and I am moving it to vertical horizontal.
So the image is moving with the lens.
Is a concave.
So it's a concave lens.
This lens, we need to take its opposite power, that is plus lens, convex lens. So I am taking some convex lenses so that I can utilize this lens. First of all, I'm taking +5 power and moving it.
So there is still some movement.
This lens is not neutralized. I'm taking the next power, that is 5.5 plus 5.50.
There is still some movement.
That means it is not utilized. Now I am taking +6 power. +6 power, and see, there is still little movement is there. I'm taking +8 power.
Is the
I-
video
No,
visible?
the video is not running.
Okay.
It ran for a while, but it stopped.
Okay.
And see, there is against movement. So
with this, with +8, he has had a opposite movement. So he's trying something in between now. So it has neutralized it around +7.
the lens is neutralized, and the finding power of this lens will be the opposite power of the lens which we use.
That is, the lens that we are using is -7 now.
This lens will be -7.
Moving on to how we neutralize cylindrical lens. This is a video showing the same.
Hello friends. Today I'm going to discuss. First of all, we need to find out what type of lens it is. So we can do this by seeing its movement. See, there is a movement, but
there is a movement in the same direction of the lens. So we know that this lens is concave.
we see the movement, it is with movement. That means it is a minus cylinder lens. And to neutralize this lens, we need plus cylinder lenses. So I'm taking some plus cylinder lenses here. And our second step is to find out the axis of this lens. I am taking a random plus cylinder lens to find out the axis.
Is the voice clear in the video?
See, there is
a scissoring movement as we rotate it. So we are slightly rotating the lens.
If you can make it full screen, it would be even better seen.
So rotation. There is also rotation.
So we keep rotating the lens clockwise till the scissoring movement stops happening. So almost here there is no scissoring movement.
We got the axis here.
So this is where we will mark the axis with the help of a felt tip.
So align it and mark it here. So this is the axis, and I am marking this axis nicely.
And then we have to neutralize it with this similar spherical power.
So this is not neutralized. I'm taking +3.50, placing it over the meridian and moving it to vertical, and I see there is some against movement is there. So it is not neutralized. I'm taking +2 power, +2 cylinder lens. See, there is movement. It is not neutralized. I'm taking +3, placing it over the meridian, and see.
Now it has been
is there. That means
neutralized.
Power of this lens will be opposite of the power of the lens which we use to neutralize this lens. It is +3. this lens is +3 cylindrical lens, so it will be -3 cylindrical lens. So let's check. Yes, it is -3 cylindrical lens, and this lens we got the power. So that's all.
So this is how we are going to neutralize the cylindrical as well as the spherical powers when we do not have a Focimeter or a lensometer. Coming on to the lensometer or the Focimeter, these are the indications. Firstly, it is used to neutralize a pair of glasses. That is, we do not know what the prescription is. Secondly, it is used to verify a pair of glasses. That is, the glasses are being made, but then what is the accuracy of those fabricated glasses? And then thirdly, it is being used for duplicating a pair of glasses. That is, we know the prescription. Now the lab has to make the similar prescription glasses. In the case of a spherocylindrical lens, it also helps us determine the axis of the cylinder. It also locates the optical center of the lens and determines the power of prism and its direction. The newer lensometers, the automated ones, can also know the power and the back vertex and the front vertex of a contact lens. So the lensometers can be used to know the front as well as the back vertex powers. For knowing the back vertex power, the lens has to face the lens stop, that is the back part of the lens has to face it. And to know the front vertex power, the front part of the lens has to face the lens stop. So lensometer systems are comprised of two parts. That is, the first part is the red part is the standard lens system. It is also known as the observing system. And then the yellow part is the focusing system, and it is also based on the Keplerian telescope. So this is a manual lensometer, and these are its main parts that we need to know. The first thing is the eyepiece, and then there is the protector ring. The eyepiece can be rotated anti-clockwise and clockwise so as to focus the reticule. The reticule is somewhere here. This is the power switch, and then we have different attachments for keeping the lens. That is why here is the lens stop. Here is the axis marker. That is, in the case of cylindrical glasses, we need to mark the axis. This is where the axis marker is. Then this is the lens holder lever. The lens stable adjustment lever is here. We have to take care of the power drum. This is we rotate it, and that's how we know the power of the lens. And this is the axis wheel, which is basically to focus the exact cylinder of the lens. Moving on. So this is a schematic diagram of how the whole system works. So if in case I'm going to divide this whole system into half, so this is the focusing system and this is the observation system. We will be going through both of them one by one. Coming to the focusing system. So let's suppose if in case I draw a line here, this whole thing is the focusing system. It has a target. So the light source is somewhere here. It has a length, it has a target, and this is the axis wheel. So from here, there are divergent rays coming, which are then converged by this convex lens, which is a standard lens of a power of about +20 diopters. From here, the parallel rays arise. Now, this is the second focus of this lens, and this is where exactly our lens table is based. So the unknown lens will be placed here. Now these parallel rays are going towards the observation system, where again there is a convex lens that converges the rays onto the graticule. Now this graticule or the reticule is what is the image seen by the observer, and this is this image and the target image have to be collapsed together. So this is just the half of the system that I'm showing. Here is the power wheel. This target is movable. It can move either towards the lens or away from the lens. And it moves when we move this power wheel. And how much we move, the readings come out here. So the focusing system is basically based on the Barrel principle, which says that if the eye is placed at the focal point of a positive lens, the virtual image of an object located between the lens and the entire focal point will always obtain the same visual angle. Coming to the observation system. So this part is the whole observation system. It consists of an objective lens, the graticule, and the adjustable eyepiece. So basically, it has two convex lenses. which have a focal point in between, and that is exactly the point where a reticule is there. So the parallel rays which are coming from the standard lens are now being converged by the objective lens onto this reticule, and what is being seen. Now, when we introduce an unknown lens here, so the image of the reticule now is defocused. That is how we have to move the target so as to focus the image of this particular unknown lens. And whatever focusing is done, whatever distance the target has to move, that is then shown on this lever. So the 2+ lenses are positioned so that their focal points coincide with each other. So this lens and this lens, they are positioned in such a way that their focal points are coinciding with each other. And this particular, like I said before, the lens stop is exactly at the second focus of this standard lens. So now we have to talk about two things, the target and the reticule. So the target can be of different types. One of them can be simply these line types, which have a single line, and there are 3 lines like this. Now, out of these lines, we have to decide that which of these will be depicting a spherical line, or which of these will be depicting a cylindrical line. So, for example, here the spherical line is a single line, and the cylindrical line are 3 lines. Then, in this particular system, these 4 cross lines are depicting the cylindrical lines, and the spherical lines are the simple horizontal lines. Again, showing the same thing, that the reticule is basically concentric circles, and the target is made up of these lines, where a single line is a spherical line and the cylindrical lines are 3 lines. Now, principle of a lensometer. Firstly, we have to set the instrument at 0, and it is when the instrument is at 0 and we do not have the lens in between, it is at that point of time that that are targeted illuminated, the illuminated target will be showing off the rays, which will be then converged by these standard lens into parallel light rays. Now, movement of the target. So let's suppose that this is a normal system that we have. When the target, when we are placing a concave lens, so the target has to be moved away from the standard lens, and whatever movement is there, it is then shown on this particular scale, and this marks the power of this particular concave lens. On the other hand, when we talk about the convex lens, this is where the target has to be moved towards the convex lens, towards the standard convex lens. So this is the power which is then shown here, and this is a convex lens or a plus lens. So this is how the reading looks like. The physical distance moved backwards or forwards from the target gives the power of the unknown lens for the meridian being used. So the black scale will be showing the plus lenses, that is the convex lenses, and the red will be showing the minus lenses or the concave lenses. Now, how do we prepare the lensometer? So firstly, the power drum has to be rotated to 0. Then the eyepiece has to be rotated to 0. So firstly, we are firstly focusing the eyepiece. So it has to be turned completely anti-clockwise, and then we have to see this reticule. So this should be focused first, and we slowly we turn it clockwise so as to get this into focus. That is the reticule into focus. Now we have to place the lens in the lens stop, and we have to see that whether or not its center is coinciding with this particular reticule. Now, these are the Myers for spherical lenses. Now we have already placed the lens on the lens stop. So firstly, if in case on turning the power wheel, if in case all 4 of these Myers are getting focused, so this means that this is a simple spherical lens and there is no cylindrical power to it. So we'll just read the value from the power drum, and that will be the power of this particular lens. But if in case while we are rotating the drum, only one single cross is getting a little focused and the other one is not getting focused, that means that we are dealing with a cylindrical lens. So in this case, we'll be rotating the axis wheel, which is for cylinder, so as to focus one of the lines properly. And we have to see that the two target Myers should be perpendicular to each other, And then we start rotating the power drum, so that at least one meridian gets sharply focused. Now, wherever that particular meridian is getting sharply focused, we have to note the cylindrical power of that Meyer. Also, whatever power it is getting neutralized at. Then again, we have to focus the Meyers perpendicular to it and note the value. So this is also a video which is telling how do we see the power of spherical and cylindrical lens in a lensometer.
To mount spectacle on manual lensometer. Mount the spectacle lens on manual lensometer's viewing platform. Place the front surface facing towards the eyepiece. How to neutralize spherical lenses? A spherical lens has equal power in both meridian and rotating of image takes place.
So there is no scissoring reflex, so there is no rotation of any image that is taking place.
Place the lens on manual lensometer's viewing platform. Move the lens such that the lens is as much as possible towards the center lying in the optical zone. Adjust the lens table.
So we are adjusting so that the optical center can be found. So we have the 4 Meyers.
Put the target sharp and clear.
And all the 4 Meyers are getting sharp. So it is basically a spherical lens that we are dealing with.
Stop rotating the power drum when the target is sharp for the first time. And note the reading.
So it's a simple spherical lens.
Also records when the lenses. Right eye 0.5 dioptric sphere, left eye plus 2.5 dioptric sphere.
Now we're talking about the cylindrical lenses. So here there is some tilting of the image.
Different power in each meridian and tilting of image takes place. Adjust the lens such that the lens is as much as possible towards the center lying in the optical zone. Rotate the power drum such that any one meridian of the Maya along
So
the
right now
dotted
only
line
this one horizontal meridian is getting focused and the other one isn't. So that means that we are dealing with a cylindrical lens.
Axis wheel such that the center dotted lines lies in parallel orientation to the right meridian.
So we are now
Rotate the
firstly
power drum where the right meridian becomes more sharp.
So here we have rotated such that the 2 lines are perpendicular to each other.
Again rotate the power drum so that the opposite meridian becomes clear.
Now the opposite meridian is getting clearer and we note the power on this axis as well.
And note the reading. How to record cylindrical lenses for left eye. Now, here we have neutralized horizontal meridian first, that is 170 degree, and vertical meridian, that is 80 degree. Note, in order to prescribe cylinder in minus form, we need to choose a spherical component to be either less minus
So here
or
we are
plus.
basically doing the notation of the lenses.
So here,
So this is how we are going to neutralize with the help of a lensometer. This was manual lensometers. The automated lensometers do not need that much of work and they work on the principle that the degree to which the light is reflected as it passes through a lens will depend upon its focal and prismatic power of the lens and the distance from the optical center. In this, we have a color LCD monitor and then the operation switches. This is a marking lever, lens plate, and the nose pad. In this, not much has to be done. The Mayas have to coincide, and then it gives the reading. The features of an automated lensometer is that it can give us the UV transmittance measurement. It can also tell us about the pupillary distance. It also measures the soft and the hard contact lenses powers as well as the vertex, as well as the vertical power, the vertex power. And space, it also tells us about, it also gives us a full screen. The settings can be customized and it can be configured with the EMR systems. Coming to Geneva lens measure or the lens clock or the Geneva lens So this is basically a gauge type, watch type of an instrument, which is used to measure the vertex power, the front vertex power and the back vertex power. A difference in between the two is going to give us the power of the lens. So it is a mechanical dial indicator that is used to determine the dioptric power of the lens. It is a specialized version of a spherometer. A spherometer is something that gives the measure of the radius of curvature of a lens. It measures the curvature of the spherical surface, but it gives the results in diopters. But for that, it assumes that the lens is made of a particular material which has a particular refractive index of 1.523. So uses is that it helps us give the correct prescription pair of glasses. It can also measure power of contact lens if special lens support is utilized. It confirms the correct radius of curvature for mounting of lenses. When we talk about the parts of the clock, so basically this is the gauge system, and then we have 3 pins here. These 2 side pins, they cannot be moved, but this central pin can be moved. It can move either outwards or inwards depending upon what surface is it being placed on. Now, when it is placed on a convex lens, it is pushed inwards, and in a case of concave lens, it will pushed outwards. Now, this particular difference in between the height when it goes in or out as compared to the side pins is known as the sagittal or the sag for the arc of a circle, which is not the exact measure of difference, but it gives dioptric power. As in, if in case we have this lens clock and we have a concave lens, now the difference in between the height of these two, that is the side pin and the central pin, is known as the sagitta. And this sagitta is to be noted, and the optical power of the surface can be calculated by this particular formula. So this is the sag being shown. This is in the case of a concave lens, and this is in the case of a this is in a case of a convex lens. So this is in the case of a concave lens. The pin has moved out, and the pin has moved in towards inwards. So this particular formula gives us the power of the surface, that is 2n minus 2s upon d upon 2 and the square of the whole. So where n is the index of the fraction of the glass, which is usually 1.523. Sagitta is the vertical difference in between the central and the side pins. D is the horizontal separation of the outer pins. And it gives the value in diopters when S and D should be specified in meters. So we measure both the sides of the lens, and it gives the approximate power of the whole lens. That is, we'll measure the power for the front curve, and then we'll measure the back curve. The difference in between the two is going to give us the power of the lens, and the radius of curvature can be known by n minus 1 power of the lens, n being the refractive index of the material. But how it is to be used is that the gauze has to be held perpendicular to the surface of the lens. There shouldn't be any tilt. If in case, and then we start rotating it. In case there is no change in the gauze, that means we are dealing with a spherical lens. But if in case there is any change in the reading of the gauze as we rotate the lens, that means that it is toric. So this is how it is to be placed. There should be no tilt whatsoever. This is a video showing how it works.
Measure a pre-existing lens curve for accurate duplication or verification. A lens measurer, sometimes also referred to as a lens clock, is used. The lens measure has 3 legs or points of contact with the lens surface. The outer 2 are stationary, and the center contact point moves in and out. A lens measure or lens clock is held perpendicular to the lens surface with the center contact point at the optical center. Tilting of the lens measure or lens clock results in a variation in the measured power.
So that will be all about the 3 ways of neutralizing the unknown lenses. We can start with the discussion now.
So, ma'am, Dr. Rupal, ma'am, would you like to ask some questions, ma'am? Otherwise, I have.
So, Shreya very nicely dealt with. It is an interesting topic. Um, you've also very nicely given take-home messages, like how important is neutralization of the lenses, where all you can make use of these particular techniques. It's good to have a lensometer or a focimeter, but if you don't have it, you can still do it. And it's in fact a very quick and nice way to know what is the power of the glasses that the person is wearing. And it can give you a fair idea about where to start your refraction from also. So it is really a good technique. You have pointed it out well. You've also shown nicely. Um, how I don't really have questions. I just wanted to know how common is the use of the Geneva um, gauge, whether it's available, and the accuracy of each of these instruments. So if you
Ma'am,
can,
Geneva lens measure is not very much available that easily. It's not that used also, but
right.
just for the historical purpose and just in case if we do not have it, we can still use it. Accuracy, the automated lensometers are a little less accurate as compared to the manual lensometers. So
Yeah.
manual lensometers still have a lot of say. And as far as the hand neutralization is concerned, it is still a very rough estimate of knowing the powers. So just to know that whether a lens is a positive, negative, or a toric lens, we can use it. But to precisely neutralize it, it's better if we go for an automated or a manual lensometer.
Perfect. Dr. Nidhi?
Ma'am, I think Dr. Shreya has already answered two of my questions. The first one was that, I wanted to ask about hand neutralization. You said it is good for small spherical errors. And you also showed us the neutralization of cylinder with hand neutralization. But in case one has the lensometer available, manual lensometer or automated, then what is the role of hand neutralization as a good teaching tool or otherwise?
I think it has more to do with the teaching purpose because let's suppose we are in a shop and right now we don't have a lensometer. At least we can tell that your lens is a negative or a positive. It has much more of theoretical value to the PG students as of such. We can just give a rough estimate of it, but then we ultimately will have to move towards automated or manual lensometer so as to have a good reading.
Yes, so rightly
It's
pointed out,
also
like especially for
quite easily
students.
available, all these lensometers and all. So I'm sure all the optician shops and everybody must be having a lensometer.
Yes, ma'am.
Secondly, you said that manual lensometers are better than automated lensometers. So that was my next question, that manual are better, more accurate.
There have been multiple comparative studies. It has been found that the ones which are actually neutralized by in manual also, at least a human is actually doing it. So it's much more accurate when it comes to neutralizing. So there have been multiple studies showing that.
And
But
also, do you have any experience in, like you showed us the centration while focusing, one would put the front surface or the back surface and center the optical part well. So in case of progressive glasses, is it easy to, get the power with the lensometer, or does it require more practice and placement of the spectacle?
With progressive, for sure, we need more. In fact, automated do better with progressives as compared to the manual lensometers, because everywhere that I have read, it was more of bifocals being neutralized than progressives in the case of a manual lensometer. So I think for that, automated does a better job.
Shreya, how do you think we can know the exact center of the lens on a glass, a spectacle glass? How do you make out where is the center of that particular glass?
Depends upon what kind of glass are we talking about. In the case of spherical, it's still easier. But when you talk about a spherocylindrical lens, in that case, the two lines should be completely perpendicular. And the very point at which they are completely perpendicular to each other, that will be the optical center of the lens. In the case of a automated lensometer, it should coincide with the reticule.
So that's very important when you're doing a manual one. you should learn this technique well, otherwise you would not be giving a correct result.
Yes, ma'am.
Do the measurements also change? Like you said that, especially with the Geneva lens measure, we are not using it. You said it measures at a particular refractive index. Does that also apply to lensometers? Would it be affected by the material of the spectacle, the measurement?
No, ma'am. There is no calculation involved in the case of a manual lensometer where we are using a refractive index. In the case of Geneva, it usually uses a particular material, and if in case there is anything beyond 1.5, it might give a lesser reading or a more reading. So Geneva lenses still have a historical significance in that sense. Especially, it's very difficult to use it very well. That it has to land perfectly perpendicular to the surface.
Yes, it
And-
seems to be very user dependent to hold it in a particular manner, and
Yes.
that's for it to
Yes,
be
ma'am.
accurate.
For normal lensometers, what is the repeatability? So are there any person to person variation? If I do it, then you do it with the same glass, would we both have different readings?
It can still be there in the case of automated, but when we talk about manual, unless there might be minor differences in between the readings of the two, but with it's much more there with the automated.
Okay. And why is it so? Why with automated you think there are?
Probably the optical center and how you bring it to the bring the two things to center in to target the two targets in the center. I think that can be a difference.
Do you expect any more advancement in this field?
I think one of the advancement that has already come in the automated ones, that they are already measuring the vertex power of contact lens and the power of contact lenses. So I think somewhere there only there would be more advances.
Right.
We don't have any questions in the chat room. There are no questions.
No, ma'am. None as of now.
So, ma'am, any remarks from your side, Dr. Rupal, ma'am?
I think it was a very clear and nicely presented talk. And Dr. Shreya, congratulations to you for this.
Thank you so much, ma'am.
You also made it interesting by the videos.
Ma'am, actually, it was so hard to explain because I could have put in a lot of theory, but that wouldn't have made any sense if, if
This
being
made
done or
sense.
shown. So,
Very
yes.
nicely thought of and nicely presented. Thank
Thank
you.
you so much, ma'am.
Especially the neutralization of the cylindrical lenses, ma'am. I really appreciated that video. It made it very simple and clear to understand.
Yes.
I'm glad, ma'am, that I hope everybody would be able to understand it, because theoretically I tried put in like by one sentence in the other, but I'm pretty sure it's still hard to grasp the concept.
Thank you. Thank you, Dr. Shreya. We thank you for today's interesting presentation. Thank you.
Thank you so much,
Thank you,
ma'am.
ma'am.
Thank you,
Thank you,
everyone.
Rupal ma'am, for your time. Thank you, Nidhi ma'am, for your time. Thank you so much.
Thank you, ma'am.